TV. I'm sorry.
That's fine. So yes, please feel free to interrupt me about the things that we're talking about. I understand people have a diverse background, so I'll try to hopefully give some useful background information to everybody. Some of it might be too basic, but also in the end we'll go through some more advanced topics. So let's just try to make the most of it. And yeah, please ask questions if there's anything that you want to kind of talk about further. Okay, so first I should point out and kind of clarify that what I'm going to talk about today are problems in computational number theory. So algorithms to solve these kinds of problems. This is different from unsolved problems in number theory. The Riemann conjecture about the zeros of the zeta function is an unsolved problem in number theory. And quantum computers really are not going to be useful in tackling these kinds of problems. Rather, what we're looking at here are, computing or computing quantities typically, or properties that we know exist. And the question is really like, well, how quickly can we perform this computation? How quickly can we figure out these properties? And so whenever people hear number theory, they always want to talk about these unsolved problems in number theory. They're very attractive because they're easy to understand and hard to solve. But that is explicitly not the topic of today. Another thing that I should make, I want to be clear about is that kind of along with the previous slide, that quantum computers cannot solve uncomputable problems like the halting problem or other uncomputable problems in, say, again, number theory, solving Fine equations, for example. And the proof is very simple because a classical simulation exists of quantum circuits. Therefore, whatever a quantum computer can do, a classical computer can do also. So that's the end of that idea. Instead, we're looking at efficiency. Now, I should also be clear that I do not think, and I think this is the majority opinion, that NP-hard problems or NP-complete problems, like the traveling salesman problem, will not have a efficient quantum solution in the worst-case scenario. And so any kind of problem in number theory, in computational number theory, that is an NP-complete problem, I do not think that there are quantum algorithms for that. And instead, we have to look at this sweet spot of problems that are hard classically, or we think are hard classically, but are not as hard as NP-hard problems. And the interesting thing is that number theory provides a fertile ground for that kind of problems, the kind of problems that we have reasonable hope that quantum computers can help us with. And so it's this kind of surprising phenomenon that when you look at the quantum algorithms out there that we think provides a super polynomial or even exponential speed up over classical algorithms, that a lot of them have to deal with number theory. And so it's kind of surprising that somehow quantum physics and number theory get along as well as they do. And so, yeah, we'll talk about, various examples of this phenomenon. Now, it all starts in 1994 when Peter Shor announced and shown his results on quantum algorithms for factoring and discrete logarithms. And so just to kind of make it clear what I mean here is that if the problem instance of factoring is a number and it's written in binary, and so the problem size is an n-bit number, and this number will therefore have a magnitude of the order 2 to the n. And so n is the size that we care about in complexity theory. And what Shor showed is that in the, using quantum circuits in appropriate model, there exists a quantum algorithm that can factorize n-bit numbers in cubic time in little n. and that what is not needed is 2 to the power some polynomial in n, some exponential time. Now note that this polynomial for classical algorithms is not linear or quadratic. It's actually it's a square root of n, or a cubic root of n. But best classical algorithm for factorization is not polynomial in n, it's super polynomial in n. And an immediate consequence of this result is therefore that if you have a fully functioning quantum computer, RSA security no longer holds because we can break that protocol. That's not if and only if. It is perfectly imaginable that we can break RSA yet factorize numbers efficiently. So factorizing is strictly hard. It could be strictly harder than RSA security. But the direction does go the other way around. RSA security is compromised by an efficient algorithm for factoring. And then there's this like poem about like how this is funny because we also know about quantum crypto, which has a security of a different kind. That's not a public key crypto system. And so crypto and quantum computing have an interesting back and forth. Here I will not be talking about quantum crypto. Instead, we'll talk about Shor's algorithm for factoring. All right. Now here we kind of go about some background material, and this varies greatly of what your specific background is. I'll be talking a bit about the greatest common divisor. So this is the function that takes two integers x and y, and it returns the largest integer d, such that both x and y are multiples of d. And so an example of this is that the GCD of 112, the greatest common divisor is 4. I did this correctly. Yes, I did. And the greatest common divisor of 101 and 12 is 1. And actually, the greatest common divisor of 101 and any integer between 1 and 100 is 1. And this has to do with the fact, of course, that 101 is prime, and therefore it doesn't have a non-trivial GCD with any number strictly less than itself. GCDs and primality are closely interconnected. And if you find a non-trivial GCD of a number like 100, you found a factor of 100. The fact that the GCD of 112 is 4 tells us that 4 is a factor of 100. So being able to figure out GCDs can be helpful when trying to factorize integers. Now, if I give you two integers, x and y, there exists an efficient classical algorithm to figure out what the GCD is. This is Euclid's algorithm. So just computing the GCD can be done efficiently. And it's simple, but it's not entirely trivial, right? You cannot just try, well, is d equals 1, d equals 2, d equals 3? Is that a solution? You have to do something slightly smaller than that. And properly understanding Euclid's algorithm that computes the GCD of two numbers is actually a good exercise for people who have not seen that before. So that's the GCD, and the GCD plays along, interestingly, with numbers that are prime or that are not prime. When the GCD between two numbers x and y is 1, we call them co-prime. So primality testing is quite tricky, but co-primality testing is pretty straightforward. Okay. Now, another thing that's important to understand Shor's algorithm properly is to understand modulo n arithmetic. And there are different ways to present this. The more mathematically, I'd say, proper way of doing it is to say, like, look, you've got the integers z, and you can do addition and multiplication over z, and that's all well defined. And now I introduce the additional rule that I consider n to be 0, and therefore 2n is 0, and so forth. What this means is if you do this, if you do all the arithmetic of the integers modulo this n, you end up with another object, a ring, where you still have addition and multiplication, but it starts to obey it has different properties. In many ways, it's the addition and multiplication that you know and love, but there are, properties that are at first glance maybe a little bit surprising. So, for example, if we look modulo 3, then 5 and 2 are considered equal to each other. So 5 equals 2 modulo 3. And if you square the sum of two terms, modulo 2, and because 2 times x and y equals 0, you have this nice property that x plus y squared equals x squared plus y squared modulo 2, something that obviously doesn't hold in general. And also, and this is going to be more important for us, is that if you're doing your calculation modulo some number, and especially if that number is a prime, then you start to get multiplicative inverses. So 2 times 7 equals 1 modulo 13, or the inverse of 7 is 2 modulo 13. Whereas clearly that you don't really have these kinds of inverses when you talk about the integers besides 1 and minus 1. Now, depending upon the community that you kind of operate in, people use different notation for this. Some people just use the standard addition and multiplication notation and just say mod n at the end of every sentence. Some people say, like, look, we just have to understand that the addition and equality and multiplication symbols should be interpreted not over the integers, but over the integers modulo n, or nz. So then it becomes this ring or finite field that you're talking about. And what is important for us is that if you talk about this ring, so now you just talk about like this, z modulo n has n elements. There's properties having to do with addition and multiplication. And these properties will vary greatly depending upon n. If n is a prime, the ring will be very different from the case where n is not a prime. So the ring z modulo 100 is very different from z modulo 101. And this is kind of a global property that is spread out over this ring. And that's the kind of global property that we might hope to extract using a quantum algorithm. Now, this is a pro tip for me. Don't write z underscore n. I don't know why this has become kind of a standard in computer science. It's very confusing because mathematicians will think you're talking about p-adic numbers and so forth. So you can really show that your sophistication by not using that notation, or correcting people who use it, as I'm doing right now. Okay. Good. So as I said, this ring z modulo n, integers modulo n, will be a different ring for different values of n. If the n is not a prime, if it is something like 100, then the numbers that are, like, say, divisors, or that have a cofactor with 100, and will not have a multiplicative inverse. There is no number x such that 2x equals 1 modulo 100. But if n is a prime, then every number that is not 0 will have such a multiplicative inverse. And specifically, in general, if you have a number y and you're operating modulo n, this y will have a multiplicative inverse if the GCD between y and n equals 1. In other words, if y and n are coprime. So 3 does have a multiplicative inverse modulo 100, but 2 doesn't, and 4 doesn't, and 5 doesn't. 4 doesn't, and 5 doesn't, 6 doesn't, but 7 does, and so forth. And what is nice is that if I have two numbers, y and n, using Euclid's algorithm, I can figure out if they are coprime. And if they are coprime, I can again use Euclid's algorithm to figure out what the inverse is of y modulo n. So computing the inverse of a number for which it exists, for which the inverse exists, modulo n, is something that can be done efficiently. And again, the keyword here is Euclid's algorithm. And all these kinds of facts that we can do this classically is efficient is important if you want to really appreciate the efficiency of Shor's algorithm, because it uses a lot of classical algorithms that are not entirely obvious when you see them for the first time. Okay. Now, as some of you or a lot of you know, that the Shor's algorithm for factoring relies critically on the ability to find a period of a function. And so it is through this period finding that the quantum component of the factoring algorithm works, but it is through the connection between period finding and factoring that it Shor's algorithm does what it's supposed to do. So there's a large component to the factoring algorithm. And this classical component is much older than Shor's algorithm. It's from Miller from 1976. And Miller showed, and this is a result purely in classical computational number theory. And Miller looked at the following. He said, like, look, I've got an integer n, and I don't know if this n is prime or maybe a do, but or if it's a non-prime, what the factors are. I have n, but I don't know the factors of n. Let's put it that way. And I have an x, and let's interpret this x modulo n, and let's assume that this x is co-prime with respect to n. In other words, the GCD of x and n is 1. We can verify this efficiently. And given that they're co-prime, I'm going to look now at the sequence of the powers of x. Now, x to the power 0 equals 1, x squared, and so forth and so on. And then at some point, this sequence has to start to repeat itself, right? Because there's only n possible values modulo n. So it has to repeat itself. And because x is invertible, it must be that it repeats itself from the beginning. So at some point, there's an r such that x to the power r is 1, and then the sequence repeats itself. And so given x and n, there's the question, what is this r? What is this value r? And Miller asked the question, how hard is it to figure out this period r? That's the question he addressed. And he showed that it was likely hard because he showed that if you can figure out this period, then you can factorize n. And so if you believe that factorizing n in general is hard, then finding the period r is hard. Now, he did something more precise. He did not only say, like, well, the worst case scenario. He said that when you pick a random x, this is typically going to be hard. In other words, the cases for which finding the period r leads to a factorization of n, that's a substantial fraction of the cases of x that has this chain of consequences. So specifically, what Miller looked at is like, well, I give you an n, I give you an x, and you figure out what r is. And if this r is even, then it must hold that x to the power r over 2 squared equals 1 modulo n. But then by the rules of standard algebra, it must be that x to the power r divided over r over 2 minus 1 times x to the power r over 2 plus 1 must be 0 modulo n. And this then suggests that one of these two terms, or even both of them, will have information about the factors of n. So the context here is that n is not prime, but it has factors that we do not know, and we want to figure out what these factors are. And what he's saying here is that, well, if we find a period and this period is even, then there is some hope that we can use this product here to distill information about the factors of n. And so what needs to go in this line of reasoning for it to bring us to the finish line? Well, first of all, r has to be even. Second of all, it should be that it is not the case that x to the r over 2 is minus 1, because if that is the case, then the above product is trivial and we did not learn anything about the factors of n. But if those two things hold, then the product gives us non-trivial information about the factorization of n. And so this observation fits on a slide. That's easy. But what he proved is that the if and the provided in this statement hold with high probability, meaning that if you pick your x at random, they have a probability, like 50%, the if and provided hold. And so you have a factor of a non-trivial factor of n. If you can solve this problem for random x, you're in business of factorizing n. And so for Miller, this was just a way of proving that finding these periods is probably going to be hard if you believe that factoring is hard. Shor took this, knew this result, and used it in the context of a quantum algorithm that does find this R period, and therefore solves the factoring problem. Okay, so sadly, recently, John Dowling died. He was a great scientist and a fine human being. It's hard to not remember him if you ever met him. He wrote a great book called Schrodinger's Killer App, and recently there was a cartoon from the Saturday morning breakfast series where the author of the cartoon kind of paid homage to John and to his book, and he kind of reproduced this text that John wrote about the factoring algorithm. And so what it says there is, Shor's factoring algorithm is a large, dry, stale, and weighty fruitcake recipe of classical number theory embedded with the hard candied citron of Euclid's greatest common divisor algorithm and the bitter Brazil nuts of the Chinese remainder theory that is then delightfully iced with a bit of light and fluffy quantum frosting. And this is very true, that the Shor factoring algorithm has only an icing of quantum computation. And really, the big part of the algorithm is, this result by Miller. And so you need to know both to properly understand the quantum algorithm. Okay. So putting this all together, the algorithm kind of works like this now. You have an integer n, and you want to find its factors. And for some reason, you already know that it's a prime number. And so you pick a random a, that's the x of the previous slides. And you compute, first of all, the GCD of a and n. Now, if you were very lucky, then a and n already share a factor, which is then revealed by the GCD not being 1. In that case, you succeeded in finding a non-trivial factor of n. That's the goal here of the algorithm, just finding some non-trivial factor. And that's going to be good enough. So in step 2, if the GCD is greater than 1, we got extremely lucky and we found a non-trivial factor of n, and we're already done. Now, typically, what happens is that we'll see that the GCD of a and n is 1, that they're co-prime, and therefore we continue to step 3. And in step 3, in one line, we claim we're going to use the quantum Fourier transform to determine the period or the order R of this A. In other words, we're going to find the smallest positive R such that a to the R equals 1 modulo n. If R is odd, try again. If R is even, we continue. If R is even, we compute the GCD of a to the power R over 2 minus 1 and n. And if this is greater than 1, we found again a non-trivial factor of n. If we were unlucky and we had a failure, we go back to step 1. And so this is a way of finding non-trivial factors of n. And so by repeating this procedure, you can find all factors of n. You throw in some probability testing and the algorithm will hold. And by Miller's result, this whole procedure works efficiently, provided that step 3 can be done efficiently. Of course, Miller did not say anything about that. Now, it's step 3, the quantum part, that we always like to talk about in our courses on quantum computing. So what does that do? Well, Shor, of course, knew about Miller's result. And he showed that using the quantum Fourier transform modulo m, you can find this period. And so really the workhorse here is the quantum Fourier transform over integers modulo m. And the period finding, and I assume that most people have seen this, so we'll go over this pretty quickly, is, you have this function f that is periodic. In our case, this f is, the exponentiation to get the sequence. But the period finding algorithm is more general. You have a function f that is periodic with period r, and it's unique within its period. So, first thing of business is, of course, creating a supposition of these values of f. And the next thing you do is you completely ignore the rightmost register. And therefore, on the leftmost register, you have a periodicity of the indices with some unknown offset s. We apply the quantum Fourier transform over this superposition, and if all goes well, that is to say, if the quantum Fourier transform got executed correctly without too much noise, we are already done with the quantum part. We measure it, and then what we can expect to see is a multiple of m over r. You do this a few times, and then you'll figure out what the m over r factor is, again using Euclid's algorithm. And once, of course, if you know m and you know m over r, you know r, you know the period. And so that's the quantum idea. And if you've seen this often enough, you say like, okay, that's how it works. But of course, the brilliance of the 1994 result is that there's a lot of details that we need to check for this to be really feasible. First of all, is this periodicity, and somehow the period fits nicely into m. Well, when you go back to how it is used in the context of factoring, we don't know this m, so we need to figure out how to deal with that. You need to know how to efficiently implement this quantum Fourier transform. You need to show that even if you have little noise, which you will always have, an approximate QFT will still do the job. And that's, a lot of more work that needs to be done. But when all is said and done, you get a quantum algorithm that factorizes n in time cubic in log n. And so, the capital N is the whole number. So log n is the number of bits involved. So we've got a cubic algorithm, an efficient algorithm. And what is funny in a way is that why is this cubic? Why is this not quadratic? The cubic versus quadratic has nothing to do with the quantum part. It has to do with this exponentiation function that we implement. And so the bottleneck for Shor's factoring algorithm lies in the classical processing that goes into creating the proper superposition. The Fourier transform is the most efficient part of the algorithm. And so it's kind of an interesting open problem if you can do significantly better than this cubic, if you can make this into, say, a quadratic function. And that's still open and could be quite a useful algorithm to have, because in practice, there's a big difference between quadratic and cubic. So that's an open problem that I'll just share with you. Now, this is for the slide of people who got kind of lost. The one slide version is that, finding periodicity of functions is kind of a big deal. You have a function, and that is the exponentiation of some number modulo n. If you can find the period, then if this period is even, there is the possibility that these terms x to the h minus 1 and plus 1 multiplied together will give you information about the factorization of n. And the classical example, now almost 20 years old, is when you take n equals 15 and you take x equals 2, then you get the sequence 1, 2, 4, 8, 1, 2, 4, 8. So you see it as this period of 4, and therefore the h in this context is 2, and you see that 2 to the 2 minus 1 and 2 to the 2 plus 1 does indeed give you 3 times 5 equals 0 modulo 15, which gives you the factors 3 and 5 of the number 15. And famously, this was first kind of experimentally shown by Van der Siepen et al. Using NMR quantum computing. All right. The article of Shor also involve the discrete logarithm business. And in a way, it's actually easier to explain how the algorithm works because you don't have to go through this whole sequence of hoops that you have to jump through. And so what is the discrete logarithm about? Well, we looked at this sequence 1, a squared, a to the power 3, and so forth and so on, modulo n. And let's think a little bit more about this sequence. Now, what we've shown is that finding the period of such a sequence is classically hard, but can be done quantum mechanically. But what other properties can we ask about this sequence that might be hard classically and that we might be able to do using a quantum circuit? And so a very natural and important problem in number theory and in crypto is what's called the discrete logarithm problem, which is the logarithm problem modulo n. And so the setting is you've got some number n, which is a large number, or a large number, and you're given a target, and you're given a generator a, and the goal is to find an r such that a to the r equals t modulo n. Now the period finding is the case where t equals 1, but now we're looking at the general case where t can be anything modulo n. And so the convention is that you call this the discrete logarithm of t base a modulo n. And it kind of helps to talk about this in slightly more general terms. We've got some generator G, and using multiplicative notation, we look at the cyclic group generated based on this G. In other words, we look at the group 1G, G squared, and so forth. And this is finite. And given this generator G and some target X in the group, the cyclic group, determine the integer the discrete logarithm of X base G in the cyclic group C. And so now it doesn't have to be modulo n. The cyclic group can be anything for which we can define this property. So you can now talk about finite fields or the groups of curves or what have you. So it's this general setting can be solved using Shor's debug algorithm, where you first figure out what is the size of this cyclic group. You can do that. And then you define a function that takes as input two integers, a and b, and it generates, and the output of this function is x to the a times g to the b. And now notice that, if the function of a and b is the same as the function on c and d, then it must hold that a minus c times the discrete logarithm of x equals d minus b. Which is another way of saying is that in this two-dimensional grid, there is again some periodicity, and this periodicity will depend crucially on what the d logarithm, the discrete logarithm is of x with respect to g. So now we do the Q of t over a grid or two-dimensional grid. We find this two-dimensional periodicity, and that then again will allow us to compute the discrete logarithm. So what is different here is that we're talking about a periodicity that is two-dimensional, but the reduction between finding this period and solving the discrete logarithm problem is relatively straightforward. So that was the other algorithm in the 1994 article by Shor. This has obvious applications in crypto. RSA is broken by factorization. Other public key crypto systems like the Diffie-Hellman key exchange protocol or the Al-Gamal protocol rely upon the presumed hardness of the discrete logarithm, so also gets broken by Shor's algorithm. And unlike our quantum algorithms, which run in time, say, polynomial, cubic in log n, the best known classical algorithms have a running time that is beyond polynomial, it's exponential. The proven running time of factoring uses the number field sieve algorithm, and that one has a running time of 2 to the power of the order the square root of log n. And the conjectured running time of that same algorithm is 2 to the power the cubic root of log n. This is conjectured, and these are very this is a very deep open question in number theory. I should state that by the standards of algorithms like the number field sieve, what I just presented is peanuts. These classical algorithms are much more challenging to understand than the quantum algorithms. And to me, that's quite inspiring, because to me, it says that, if you could raise our game, if you can start developing quantum algorithms that really uses the full machinery of, what we already know in computational classical number theory, we should be able to find stuff that goes far beyond what we already know. There's a lot of room here to make progress. Now, what I showed on the previous slide, those are existing algorithms, and we know the running time. We do not have a strict proof that there is no classical algorithm that is efficient for vectoring and discrete logarithms. And you will find very respectable people in computational number theory who actually think that there are classical algorithms for factoring of discrete logarithms. I think these people are in the minority, but it is definitely possible. And so that would be kind of a bummer, because then all of a sudden, what we thought was an exponential separation between quantum and classical algorithms disappears. But proving these things in computational complexity theory is extremely hard. We have a great track record of conjecturing things, but very little of proving things. But what should be pointed out is that at the core, the quantum algorithm does a period finding algorithm. And we've known now since 2004 that the period finding as such, where you treat the F as a black box, that is hard. That if you don't know anything about the function except for that it is periodic, and unique within the period, that classically the best you can do is an algorithm that effectively tries things different periods and hopes for the best. And that is the best you can do, and therefore in this black box setting we've got a lower bound of n to the cube root of n, whereas quantum we can do this in a polylog n. So in that case we can prove that quantum mechanically we have an exponential improvement over the best classical algorithm. Okay. This might be a good point to see if there are any questions before we continue talking about other algorithms besides that have been developed since 1994.
I don't see any questions at the moment.
Questions? Okay.
No, not right now.
Okay. Thanks. Great. So what other quantum algorithms are out there? I would recommend for people interested in this to visit Stephen Jordan's quantum algorithm zoo. You Google quantum algorithm zoo and you'll find it. There's a great list of algorithms that solve well-defined problems in number theory, computational algebra, stuff like that. And he does a good job maintaining this site and giving the proper references. For background information as to some of these algorithms for algebraic problems, there's this article that Andrew Childs and I wrote a while back. There are other articles out there. What I like about studying my own work is that I use it all the time, because I tend to forget all these details, and the technical details are kind of given in this review article. So what are some examples of algorithms besides factoring and discrete logarithms? Well, simulating quantum physics, we knew that. Discrete logarithm, already talked about that. The logarithm over elliptic curve groups, I'll say a few things about that soon. Counting points over finite field curves, Pell's equation, the principal ideal problem, unit and class group problems. These last set are problems having to do with number fields. Approximating Gauss sums, that is a approximation problem in again, number theory. There are topological invariants which somehow touch upon number theory, although most people would not consider this a problem in number theory. And then there's lots of polynomial speedups. The way to go about extending our set of algorithms to go beyond Shor is, well, I mean, it was a very fruitful approach, because it gave us, ideas as to like, well, what's next. So one of them is, to find at the core, it's the periodicity problem that is solved by Shor's algorithm. And so, can we do more general? This is the whole idea of like, well, finding hidden symmetries, and the hidden subgroup problem has to do a lot with this idea. Well, the other one is, well, there was this chain, how we went from periodicity problem to these other problems like discrete logarithms and factoring, and can we what else can you do with the periodicity problem? And so, yeah, going back to the cake that we talked about earlier with the quantum frosting. Yeah, it's, if you want to work on this in this field on quantum algorithms for problem in computational number theory, you have to know number theory, which, if you like it, is a lot of fun. It's a beautiful field, but also, of course, it's extremely old, much older than quantum physics, and so there's a lot of stuff that that is known and that you kind of want to know about before you can make some contributions. And so you have some buzzwords that you kind of want to be familiar with when you go into this business of coming up with algorithms for number theories, that you want to know about modular arithmetic, finite fields, commutative algebra. You want to know about elliptic curves and why we care about them, function fields, class fields, number fields, groups, algebraic geometry, and so forth. So there's a lot of beautiful math that you want to familiarize yourself with before you can have I would say, a chance to find new applications of quantum algorithms for these fields. So one kind of nice example is that of elliptic curves. An elliptic curve, they're beautiful objects, but if you put it in a kind of more mundane fashion, you can say, well, the elliptic curve is determined by a cubic equation where in two variables, like in some normal form, you can write it as I give it here. And you've got this equation, and it has additional multiplication, so you can start interpreting this over the reals, over the complex numbers, or over the finite fields. And the interesting thing about elliptic curves is that the equation dictates to a large degree the properties of the curve. And so it will share, if you look at this, the solutions of this equation over the complex numbers, it will have properties like, the fact that there's a genus 1 that is shared with, if you look at the solutions over the finite fields. So you can study this elliptic curve without referring to the field over which you interpret this curve. And so this allows for the following, that you can draw this curve, make pictures of it, the reals, and then reinterpret what we've just drawn in the situation where the curve is defined over a finite field. And so the curve, the elliptic curve, is not just the shape of this plot here. It is also the fact that you can define something which is called the addition of the points on this curve. And there are many ways how you can do this, and kind of a nice picture of it is as the following, that you define the following operation. I have the curve, and I have a point P on the curve, and I have the point Q on the curve. And I want to define the operation that kind of says, well, what does it mean to add P and Q? Now, the way this works in this picture is that I draw a line from P to Q, and I look at its third intersection point, R. This is a cubic curve, and so, modulo extreme cases, there is going to be this third point, R. Next, what I do is I mirror this point R in this picture along the x-axis. And so we have now this opposite point, and we declare this point to be P plus Q. So that's kind of a strange way of defining addition, and there's a very good reason why this holds. Can't quite go into that, but this is how you can define addition. And so when you do this, you can see that, yes, you can define, like, given a point P, you can define a point like minus P, and it commutes, and it's associative, and this is all properly defined. And so we have now, using this addition and the points on the curve, we have an abelian group. This is an abelian operation, which is defined in a very unusual way when you see it for the first time, but it's a group like any other group. And if the curve is defined over a finite field, this group will be a finite group, finite abelian group. And if we have a group and it's finite, and we can define something like the discrete logarithm again, except for now, rather than addition, we use multiplication. Sorry, rather than multiplication, we use addition. And so the discrete logarithm problem for an elliptic curve is you've got some curve over a finite field, you give it 2 points, P, and a target T. And the question is, if I started with P, and I then calculate 2P, 3P, 4P, and so forth, what is the integer R such that P plus P plus P, like R times, equals T? This is the discrete logarithm problem for elliptic curves. And this is hard, classically. Well, we don't have proof of that, but we tried really hard and we cannot find a algorithm. And remember in the I've been talking about classical algorithms, classical heuristics for discrete logarithms modulo n. The discrete logarithm problem over an elliptic curve is people feel that this is harder. It's harder than doing the discrete logarithm modulo n, and that the best known classical algorithm is, has a running time that's the square root of the size of the finite field. This fact that it is harder, and therefore harder to compute for smaller instances, means that if you build a crypto system based on this discrete logarithm idea, you can get away with smaller keys. And that's why, we have got crypto based on these elliptic curves. Shor's algorithm, however, can be adjusted to this new setting, and the period finding algorithm can be, applied in this context. And we do indeed have a quantum algorithm that calculates the logarithm problem over a finite field curve, and therefore these crypto systems that use this elliptic curve setting are also broken by Shor's algorithm. And to be certain that that the quantum algorithm can be extended in this setting, you kind of need to do some legwork to kind of like check that the interference is still there, that you have unique representations of the elements and so forth, but you can make that all work. And so elliptic curve cryptography is also broken by the period finding idea of quantum algorithms. Now, pushing things a little bit further about curves over finite fields, there's also the following algorithm, quantum algorithm by Kedlaya, and that one tackles the following problem. So we're doing things over a finite field, and we look at a curve f that in 2 variables over this finite field. And this is an algebraic equation, and it's non-singular and has all the right properties. And we now ask ourselves, well, how many solutions are there in the plane fq squared to this curve? How many points does this curve have? The problem parameters of this problem is the size of the finite field q. Now q is p to the r, where p is a prime, r is an exponent, and the degree of the polynomial f. This problem gets much harder if the degree gets to be much bigger. The best known classical algorithms are either exponential in the degree or they're exponential in log q, as it were. So this polynomial in p. So that's the best known classical algorithms. What Kedlaya showed is that there's a quantum algorithm that is efficient both in the degree of the function f and in the logarithm of the size of the finite field. And so this algorithm counts these points in a way that we do not know how to do classically, and very, very well studied problem in classical computational theory. And so the article is really nice, and it refers to zeta functions over curves. So the math involved here looks at the function fields that are defined by this polynomial f, and then you define a zeta function for these function fields, and understanding the solutions to this zeta function allows you to count number of points. It's not at all a straightforward algorithm, but it's very beautiful. And so, if you're into this kind of stuff, I really recommend reading up on this algorithm. Now, another, and this will probably be my last set of examples, has to do with number fields. So I mentioned earlier finite function fields, finite fields and function fields. And number fields are constructed the following: that you take the rationals and you're going to extend the rational by some kind of algebraic root, a solution to a polynomial equation. And you're going to do, all your algebra, addition and multiplication, with q and this additional term. And so, for example, if I take q and rationals and I add to that the square root of -5, then of course, I can look at the terms a plus b times the square root of -5, where a and b are rational numbers, and you'll realize that this is a field, that addition and multiplication are properly defined for this new field, and it's a field just as the rationals are a field, but it's kind of richer than the rationals. And for any algebraic root, you can do this extension. So there are many number fields. And the trivial one is the rationals that we know and love. And so just as we have rational numbers, we have like integers. Now for these number fields, these extensions, we can also define the integers. And so the notation there for that is, the integer z, but not the regular integers, the ones that come from the number field k. And things get interesting very quickly because, for example, when you look at this extension by the root of the square root of -5, you have the integers 3 and 2, and you have the integers 1 plus the square root of -5 and 1 minus the square root of -5. And so factorization is no longer unique. The number 6 can be written as the product of two integers in different ways. And so to understand how this is and to which extent, the uniqueness of factorization breaks down with these extensions, that's like a well-studied topic in number theory. And the higher the degree of alpha, the more complicated this gets. But already if the degree of alpha is 2, if alpha is just the solution to a quadratic equation, things get quite interesting. In the context of quantum algorithms, the following is a nice example that when you have a number field, you can look at the units. Those are the integers that have a multiplicative inverse. So traditionally, the only multiplicative inverses are 1 and -1, and that's it. But for these general number fields, these things get more rich. And so, for example, if we look at the integers, but now, well, the rationals extended to the square root of 5, you see that 9 plus 4 times the square root of 5 times 9 plus 4 times the square root of 5 times 9 minus 4 times the square root of 5 equals 1. And so the 9 plus or minus 4 times the square root of 5 is what we call a unit in these integers. And when you do the math, you will see that if that is a unit, then all of its all of its powers are also units. So now we have a whole family of units of terms of the kind x plus y times the square root of 5, and that by the properties of the plus and the minus in front of the 4, it holds that these are solutions to the equations x squared minus 4y squared. This is Pell's equation. And so the problem of Pell's equation in the case here is that you've got this coefficient 5. Now you want to know what are the integer solutions to the equation x squared minus 5y squared equals 1. And this is now interpreted over the integers. Finding these solutions in general is believed to be hard. And finding these solutions is closely related with the problem of if I have some alpha, and the alpha here is the square root of 5, what is the shape? What does that unit group look like? And so what Sean Halgren showed is that quantum mechanically you can do this. He relates this to a periodicity problem over the reals, which was a significant extension over the standard periodicity problem. And he showed that if you can find the period over as defined over the reals, then you can find effectively the generator of this unit group, and therefore you can find the solution, approximate solutions to Pell's equation. And so the problem here is, given in general a term D, describe to me in the appropriate terms the structure of this unit group. And what Halgren showed is that this can be done using a fair amount of classical computational number theory, and then a significant extension of the period finding algorithm. Okay, so this is the right time to kind of ask ourselves what's next. There are a lot of problems out there in computational number theory that we kind of understand classically, but really not many people have looked at quantumly. And so 3 sources that I can highly recommend to learn more about this is the free ebook by Victor Shoup on computational number theory, a great book, a classic by Cohen, a graduate course in graduate text in mathematics, course in computational algebraic number theory, and also often when we talk about these kinds of problems, we talk about problems in commutative algebra. So you have the business of ideals and varieties, and there's a great book by Cox, Lell, and Xia that I can recommend to learn about algorithms, classical algorithms for that to understand better what the problems are there, and then hopefully succeed in finding quantum algorithms that do better than best known classical algorithms. And with that, I'll thank you for your attention. I'll be happy to take any questions.
Okay. Thanks for a very interesting talk. And I wait for questions. You can write them down in the chat section and I will read them out. So I have a first question from Prosper. Is there a quantum algorithm for solving the quadratic residue problem?
The quadratic residue problem, let me see. That can mean several things. I would say that, as far as I understand, there is a class algorithm for the quadratic residue problem. I'm going to stop sharing and maybe try to see the chat if that's okay.
Yeah, sure.
Yeah. Yeah, here we are. Okay. Can you remind me how I see the chats? Sorry about this.
It's like a third icon from the right. So in the middle you have participants, and then immediately to the right you should.
WebEx. Okay. While I struggle with this, maybe there's another question.
So, so do you see questions, or should I read this?
I don't see the chat.
Okay, so so maybe let me read another question from Carlton. Given we often have rely on claims of the form best known classical algorithms, when considering less well-studied fields, number systems, is there a risk that fast classical algorithms exist but less time has been invested in finding them?
Yeah, so I would say that I think that in general this is a good thing to be aware of. The field of computational number theory kind of in disguise, has been around for quite a while. When you look at, Euclid's algorithm and the Chinese remainder theorem, it's obvious that people have been thinking about this for a long time because they had to do these computations by hand. So I would say that the classical theory of computational number theory is extremely well developed. In a way, it's you could say that it's much older than standard business of NP completeness. So that's of course not proof, but there's a lot of thought went into finding these kinds of ways of computing these number field properties. And so if something is declared hard in that field, that definitely has some standing. Like people thought about that for quite a while and did not find the algorithms.
Okay, thank you. There's another question from Nathan. Are there quantum algorithms for algebraic problems that do not use some form of period finding?
Yeah. Well, I feel that there are approximation algorithm. There are approximation problems that have to do with in number theory, having to do with zeta functions. This is one of my favorite topics, and so I think that our the unitary matrices and group representation plays a pretty big role in number theory. There's all sorts of beautiful connections between random unitary matrices and properties of random elliptic curve, for example. And so I think that if somebody wants to kind of really go out there and be daring, I would recommend reading about this connection between representation theory and number theory. And there must be stuff out there that goes far beyond period finding, and that's then really in the context of not exact computation but approximate computations of things that are hard to even approximate in number theory. So that would be my advice.
Thanks. Another question. Is there another way of solving the factoring problem using a quantum algorithm, like adapting the number field sieve?
I don't know if people have looked into this. It's not obvious to me. Let's put it that way. It's not obvious to me. And if it were obvious, if you would do better than the cubic result of sure. I would say I definitely think there's a legitimate question to ask if we can improve significantly on the cubic complexity, but I don't know. It's not obvious that studying the number field sieve is the way to go to get there.
Okay, thank you. Are there any other questions? I don't see any other. So let's thank Wim again for a very interesting talk and discussion. You're getting a lot of virtual applause now.
Okay, thank you, because I'm
Oh,
struggling
wait.
with
Oh, wait. There is another
Okay.
from William. Is there a quantum algorithm for primality testing that takes log n time?
Is there? I don't think so. I don't think so. I think if you want to do primality testing, just stick with the try and true classical algorithm.
Okay. Maybe final question. Prosper is asking whether we can get access to the slides.
Yes, I'll be happy to share this.
All right. So if you can send me or Patrick, then we can attach the slides to the presentation.
Yeah, happy to do that.
Okay. Thank you very much.
Thank you.